In previous videos, we saw that this limit here is pretty special, and we saw what its value is as we took higher and higher values of n on a calculator, and we saw that in the limit as n goes to infinity, that this actually is equal to this irrational number we know as e. And in this video here, I don't want to use a calculator. I want to use some calculus tools in order to establish this fact. So what we're going to do in this video is do some limit manipulation. We are going to transform. We are going to mess with this limit here and get it into the form. I claim that we can get it into the form of a derivative of a function that we know. So our goal is to take this limit and transform it and get it into the form of the derivative of a function. So as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. All over delta x. And again, this is just the definition of the derivative. So again, we're going to try. I want you to try to pause the video and get this limit into a form of a derivative of a function that we know. And I'll give you a few hints to get you started. So again, you can see that there's a moving exponent. Well, when we have moving exponents, it would be a good idea to use some log rules to try to get rid of that moving exponent. So I will leave you with that. Pause the video and see if you can play around with this and try to get it into the form of a derivative of a function that you know to establish this fact that this is indeed e. All right, assuming that you've given it a go, again, we want to transform this limit here, and we're going to mess with this moving exponent first. So let's just remind ourselves of some log rules before we begin. Some log rules. We know that a log rule for a specific log rule that we might be interested in with moving exponents is that when we take the natural log of x to a power, say n, that we can rewrite this, we can bring this exponent out front, and this becomes n times log x. So that's one log rule that we can use. Another log rule is that when we take e to the natural log of x, that this is just x. So we're going to use these log rules in order to play with this limit. So let's bring this limit down and start messing around with it. Let's see. So we have the limit as n goes to infinity of 1 plus 1 over n to the nth power. And I'm going to first rewrite this using this log rule here. So I'm going to take e to the natural log of this limit, e to the natural log of this limit here, as n goes to infinity of 1 plus 1 over n to the nth power. And we have this here. And now that we have this, this is a little subtle, but I'm going to claim that we can actually rewrite this using this thing where we can actually take that the natural log of the limit is the same as the limit of the natural log of something. So I'm going to rewrite this under this equality here, that e to the limit of the limit as n goes to infinity of the natural log of 1 plus 1 over n to the nth power, that this here is equivalent. And I'm not going to prove this in this video, but maybe I can give you some intuition behind that. If we were to come over here and just write out, let's just say that we have the natural log of the limit as n goes to, let's say, 100 of 1 plus 1 over n to the nth power. And we are saying that, okay, here's the natural log of the limit. We're saying that this is equal to the limit of the natural log. So the limit as n goes to 100 of the natural log of 1 plus 1 over n to the nth power. And now if we were to evaluate both sides, we could see something that this is the case. So just evaluating both sides, we'll evaluate this limit. We have 1 plus 1 over 100 to the 100th power, and we are taking the natural log of that. And then on this right-hand side, we just write the natural log of 1 plus 1 over 100 to the 100th power. And you can see both sides agree. So hopefully that can give you some intuition that we can take the natural log of the limit, and that is equal to the limit of the natural log. And why would we want to do this? Well, now we can use this log rule. That's why we can use this log rule now on this limit. So we are going to now deal exclusively with this limit here. We're going to deal exclusively with this limit. And again, now we can use this natural log rule. So what we're going to do is write this limit and play with it a little bit. So this is the limit as n goes to infinity. And again, I'm going to use this log rule. So I'm going to bring this n, I'm going to bring this exponent out front. So this is now n times the natural log of 1 plus 1 over n. And now what we want to do is think, okay, we're getting closer, but we still need to get it into this form of this derivative of a function. And you can see there's one major difference, and that is the limiting factor here. We have a delta x going to 0, so we have something getting really small, and then we have an n going to infinity. We have something getting very large over here. So we need to fix that. And how do we go about fixing that? Well, we can actually make a substitution, and I'm going to recommend that we make the following substitution. Delta x, we let delta x be equal to 1 over n. And why would this be good? Well, when we take the limit, so as we take the limit as n goes to infinity of 1 over n, well, as n goes to infinity, 1 over n is going to go to 0. And then if we're going to make this substitution, we need these things to agree. So the limit as delta x goes to something of delta x, that also needs to go to 0. So what limiting value needs to be down here? Well, delta x needs to go to 0 in order for delta x in the limit to go to 0 as well. So now these agree. This will go to 0 as well. And now we can make this substitution. So before we do that, again, you can quick multiply by n and divide by delta x, and you'll find that n is equal to 1 over, I wanted white there. 1 over delta x. And now we can rewrite this limit in terms of delta x. So we find that this limit is now equal to the limit under our substitution as delta x now goes to 0, and we said that n was 1 over delta x times the natural log of 1 plus delta x. 1 plus delta x. That is our substitution that we made. And now you can start to see, okay, now we have the right limiting values that we want. And if I were to rewrite this maybe one more time here. So this is the limit as delta x goes to 0. And if I were to rewrite this, let's say I rewrite it like this, ln of 1 plus delta x, and all of this is going to be over delta x. Maybe this form looks a little more familiar, and you can see, okay, we're very close. The only thing that we're missing is this f of x. What is f of x? Well, if you do some pattern matching, you can see that this is the natural log of 1. So minus the natural log of 1. And why can we just add or subtract something? Well, the natural log of 1 is 0, so it's perfectly legal to add or subtract 0. So now we got it into the form that we wanted. This is now representative of a derivative that we know. And what is that derivative? Well, it's the derivative of the natural log function evaluated at 1. So the derivative of the natural log function evaluated at x is equal to 1. And maybe this notation is new to you. Maybe you're more familiar with letting f of x be equal to the natural log function. And then this is saying we want to find the derivative of that at 1. So these two things are equivalent. And going down here, the derivative of the natural log function, we know that is 1 over x. And we're still wanting to evaluate this at x is equal to 1. So we have 1 over 1, which is 1. And this is getting pretty exciting because what is this 1? Well, we are finding the value of this limit, which we found up here. And if we were to just now rewrite this, this is e to the first power, which is just e. So we can see we have successfully shown that this limit here is in fact e, and we didn't need a calculator to do so, and we've established this now. And in the next video, what we're going to do is continue working with this definition of e to solve some APR problems.